Hi everyone, in this video we're going to look at section 25.4, the definite integral. Okay, so first, what is a definite integral? In the previous section, actually let me put this over here, in a previous section we looked at the indefinite integral. And with an indefinite integral, the function or the integral sign doesn't have those numbers, the a and the b on it, and we still have that f of x dx, and the answer is the antiderivative of that function plus a constant c. So when there's no a and b bounds right there, that is called an indefinite integral, and the answer is a function. Okay, that's a key thing to know with indefinite integrals. Okay, now in the previous section, when we talked about area under a curve, what we were introduced to, although I didn't call it that yet, what we were introduced to is a definite integral. So when I have my integral sign there and the a and the b kind of stuck at the top and bottom of it, that is called a definite integral. And there's my function dx, and the answer, okay, is capital F of x, the antiderivative, but the difference is we evaluate it at a and at b, and they are subtracted from each other. So it's the antiderivative capital F of b minus capital F of a, and that is a definite integral. And ultimately, the thing to contrast here, the answer to a definite integral, the answer is a real number. The answer is a number. Okay, so two important distinctions to make. And then also in the previous section, what we saw was that when I have a definite integral from a to b of some function, that answer, that real numbered answer, is the area underneath that curve between a and b. Okay, that's a definite integral. And then one other thing I just want to add here, when you see this notation, this integral sign f of x, the way to kind of think of that, read that in your brain or out loud is the integral from a to b, put the quote signs there, the integral from a to b of f of x dx. That's the way that you kind of read that out loud. And then just recall that the dx there, that just is the variable that you're integrating with respect to. Okay. So in this first example from the section, we have the integral from 0 to 2 of x to the fourth dx. And when we evaluate that integral, the first thing we do is we take the antiderivative of the function. That's the capital F from the previous slide. Now that is x to the fifth over 5. Add 1 to the exponent, divide by the new exponent, and that gets evaluated, vertical line, from 0 to 2. X to the fifth over 5 evaluated from 0 to 2. So we're going to take 2 to the fifth divided by 5 minus 0 to the fifth divided by 5, and that is 32 fifths. 32 fifths, or what is that, like 6 2/5. Okay, and then what does that actually represent? So that's the answer to this question. What does that actually represent? If I look at the graph of x to the fourth, it basically it has a parabolic shape. But let me just sketch a little graph in there. Okay, and that parabola, x to the fourth, if I look at it over the interval from 0 up to 2, the area of that region is 32 fifths square units. So that's what you're finding when you're evaluating that definite integral. We will look at two examples on this next slide. This first example is kind of interesting in that you're going from a point 3 to 3. So it's the integral from 3 to 3 of x plus 2 dx. And we'll see what that looks like in the answer or as we go through it. So we take our antiderivative first. Integral of x is x squared over 2. The antiderivative, add 1 to the exponent, divide by the new exponent, and then plus 2 times x, 2x. The integral of a constant is a constant times x. And that gets evaluated from 3 to 3. Weird that it's the same number, but again, we'll see what happens. So we plug in our top bound, 3 squared over 2, or maybe you already see what happens. We'll see. Plus 2 times 3 minus, well, this is going to be the exact same, 3 squared over 2 plus 2 times 3. Oh, that's a little bit weird. 9 halves plus 6 for the first parentheses minus 9 halves plus 6 for the second parentheses. Okay, well, that all cancels out and gives you 0, right? Which is strange, but you can have an integral evaluate and leave you with nothing. Excuse me, and leave you with nothing. And visually, looking at the graph, what's going on here? If I have the y equals x plus 2 is a line that goes like that, and that's 2, and the slope is like up 1 over 1. And in this problem, we were looking at it over the bounds from 3 up to, well, 3. So what is the area? Now that's just a line. There's no rectangle there. There's nothing there. It's just a line. So that's why we get an area of 0. So the integral from a to a, any number to itself of a function, is going to be 0. All right, in this next example, we're going from 1 to 3 of x to the negative 2 minus 1 dx. So again, our antiderivative, take this first term, add 1 to the exponent, divide by the new exponent, minus antiderivative of 1 is x. That gets evaluated from 1 up to 3. Plug in the top bound first, 3 to the minus 1 over minus 1, minus 3. Whew, there's a lot of negatives in there. Minus 1 to the minus 1 over minus 1, minus 1. There's a lot of negatives in there. So you could use your calculators to simplify, but, well, since I'm the one doing the video here, let's see. This makes this answer negative. That puts the 3 in the denominator. Negative a third minus 3 minus, this makes the answer negative. This puts the 1 in the denominator, but 1 over 1 is 1, minus 1. All right, inside of the second parentheses, that's negative 2. And then because I have my minus negative, that becomes addition. Okay, so we're almost done here. Negative a third minus 3 plus 2 is negative a third minus 1, which would be negative 1 and 1/3, or how about negative 4/3 for my answer on that one. All right, now with this next example, we're going to encounter something a little bit different called, as it says at the top of the slide, substitution. We're still taking an integral. We're still evaluating an integral. In this case, they're indefinite. Notice there's no numbers there. So these are indefinite integrals on this slide. But we're going to use something called substitution. Okay, and I'll introduce it through this example. But basically what we do is we change everything in the integral that has x's in it to something with u's. Okay, and the purpose for that is it's a way to undo something that the chain rule did in taking a derivative. That's kind of the way that I like to describe it, at least. But it's a way to make a complicated integral slightly less complicated. All right, and so what we look for is groupings, things grouped in parentheses. So notice in this one, I have my x squared plus 1 in parentheses. Okay, and I'll show you how this works, again, through the example. So I'm going to say, and I'm going to let u equal what's inside that parentheses, x squared plus 1. And then I'm going to take the derivative of that. So I'm going to take on the left-hand side du, the derivative of u, and on the right-hand side, I'm going to differentiate. The derivative of x squared, exponent comes down, subtract 1 from the exponent, and then the derivative of 1 is 0, plus 0, and then we tack on a dx at the end because I'm taking the derivative with respect to x. And if you don't see where that comes from, remember the other way that we wrote our derivatives when we go from y to y prime, we take du over dx is equal to 2x is another way to write that. That would also be correct. And we just take that dx, multiply by dx, and put it on the right-hand side. I don't write it this way every time. This is the way I show it. Okay, so du is equal to 2x dx. All right, and now the purpose of all that, watch what happens. Inside of that parentheses is my u. All right, inside the parentheses is my u. So I'm going to substitute that parentheses, leaves behind a u from my substitution. And after the parentheses, the 2x dx, well, that is everything that is equal to du. 2x dx, 2x dx, du. So I'm going to take and substitute that du in for 2x dx. So we've pulled everything that just has x's in it out and replaced them with the appropriate u and du. Now this integral looks way less complicated. The integral, the antiderivative of u, is u squared over 2. And because this is indefinite, there's no bounds, I tack on my plus c. The additional step that we have to take, though, is my answer. I don't want to leave u's in my answer because the problem was given with x's. So I'm going to substitute x squared plus 1 in for the u. This u right here is equal to the x squared plus 1 right there. And then don't forget your plus c. And so there is my answer. And if you look at that and check it with a derivative, if you check it with a derivative, you'll see what I mean about it undoing something that the chain rule did. Because the derivative of the outer, where the 2 comes down, it cancels the 2 in the denominator. And then the derivative of the inside is the 2x. Okay, so that's what I was talking about there. With the other example at the bottom, we'll do that one the same way. We'll look inside the parentheses first. If I take and set u equal to x squared plus 1, then, and I'm not even worried about the 3 there, by the way, right now, the cubed, just what's inside the parentheses. Then du, just like the last problem, is 2x dx, same as the last problem. So I make my substitution, and, oops, I don't need a parentheses there. X squared plus 1 is equal to u, but it's still cubed. And everything after it, 2x dx, is the du. This equals u to the 4th over 4 plus our constant c. And then we go and back substitute x squared plus 1 to the 4th over 4 plus our constant c. All right, so that's the work of that problem. And then just to kind of compare why the u substitution is useful, in the first problem, if you go back to the way it was written at the beginning, that function, it would have been reasonable to take the 2x, distribute that in. Maybe you even thought to do that. I didn't even mention it until now. Take the 2x, distribute it in, and use our regular antiderivative rules. Sure, fine. But this guy here, well, with the cubed there, would have been a bit more involved to expand all of that out. And with u substitution, we don't have to worry about that. In the next example, we get a problem where we're going to use a u substitution again. This one looks different than the previous one. However, we're still going to look for that grouped guy. Hold on, you got my highlighter there, but that's okay. What's grouped under the square root sign. And we're going to set that equal to u. Not the whole square root term, though. U is equal to just what's under the radical sign, just the stuff grouped together, x cubed plus 2. All right, that's important. If you do the radical and then you're doing the chain rule within your substitution, no, that just makes it worse. All right, and then du, the derivative, is 3x squared dx. All right. So that's our u work. But what you notice here, and what makes this one, other than the square root, what makes this one a little bit more challenging is, let me get my highlighter, there's a 3 here. There's not a 3 there. That's a little bit weird. Okay, so why it's not a perfect one-for-one substitution. But what's cool and what ends up happening is if I write that 3 on the other side, and how do you bring a 3 to the other side of the equation? You divide by it. 1/3 du is equal to x squared dx. Now I don't need to, now the 3 is, it's part of, I bring the 3 into the integral because it's not there already. I just bring it in the denominator. Okay, so what do I mean by that? Well, let's take a look at where everything goes. My integral sign stays my integral sign. Underneath the radical is x cubed plus 2, so u is underneath the radical, and my radical sign's too long. Underneath the radical is just u. Outside of the radical, I have an x squared. I have a dx. Well, what is that equal to? It's equal to 1/3 du. And I could write that in whatever order I want to. I'm going to choose for now to write it after. 1/3 du. Okay, that looks a little bit messy. Let me write it a little differently in my next line here. That equals that. That equals the integral of 1/3 u to the 1/2. I'm bringing that root up as an exponent. Du. All right, great. Now we're ready to take our antiderivative. 1/3 u to the 3/2. Check that. 1/2 plus 1 is 3/2 over 3/2. No bounds, so we write plus c. 2 more steps. Clean it up, back substitute. So this equals 1/3. I don't like that fraction in the denominator, so bring it up. When it comes up, it flips over. So times 2/3 u to the 3/2 plus c. I'll multiply my fractions, 2 over 9, and then back substitute, x cubed plus 2 to the 3/2 plus c. I guess that one was a little bit more involved. Go back, check it, watch it again if it didn't make sense. But these can get a little bit more complicated as we start moving through here. Okay, now our last example of the section. First thing to notice, it is a definite integral. There are bounds. My answer is not a function. My answer is a real number. It's an area under a curve. Second thing to notice, parentheses to the 5th power, stuff out in front. Okay, we might want to use the u substitution, and we will. Okay, so I'm going to take and set u equal to the stuff that's grouped together inside of the parentheses, z squared plus 1. Not to the 5th, just the z squared plus 1. So du is 2z dz. dz. Okay, so here's u, z dz. That's good, but I don't have a 2. I've got a 5. Kind of looks like a 2, but it's not exactly. So same as the last problem. I'm going to take that 2, write it on the other side of that equation. 1/2 du is equal to z dz. All right, and then we have our integral. Okay, so we make our substitutions. Our integral, I'll come back to the bounds just a moment, okay? Our integral, 5 stays, times, let's see, z squared, or no, it's not z anymore, u to the 5th, and then my 1/2 du. Just to make sure that we see where everything comes from. Z squared plus 1, z squared plus 1, u. Follow the yellow highlighting, and then let's go green. Z dz, z dz, that is 1/2 du, 1/2 du. Hopefully you followed that. Now the bounds. For the bounds, I'm going to do something a little crazy. No, it's not crazy. It's actually like normal. It's how you do these. For the bounds, see the bottom bound is 0 there? That's a z bound, right? Those are z's in that top integral. Top bound is 1. That's a z there. That's a z bound. I'm going to get new bounds. I want to write my bounds in terms of this u that I've introduced. How do I do that? I go to the original substitution right here. U equals z squared plus 1. So for my bottom bound, u equals 0 squared plus 1, which is 1. And for my top bound, u equals 1 squared plus 1, which is 2. So the old bounds are from 0 to 1. The new bounds are from 1 up to 2. So let me rewrite this once without the highlighting. Integral from 1 to 2. 5/2, I'll write that as one single fraction, u to the 5th du. And now the cool thing about rewriting my bounds like that, when I go and take my antiderivative, 5/2 times u to the 6th over 6, evaluated from 1 to 2, those are u bounds. This problem, I don't have to back substitute because I've written the bounds in terms of u. Okay, if I left it 0 and 1 for the z bounds, I would have to rewrite I would have to back substitute. But because I changed the bounds to u, I don't need to do that. All right, so let's see what we get here. 5 halves, I'll leave that out in front, times 2 to the 6th over 6 minus 1 to the 6th over 6. Punch that into your calculator, see what you get. I got 105 over 4, 105 quarters, or better known as $26 and a quarter, 26.25. All right, that is the end of that section. I hope you watched the whole thing. If you have questions on it, if you want to see more examples of U substitution because that's a little bit wonkier, let me know. Thank you for listening.